Welcome everyone, and from this video what we are going to do is start with some second order equations. Yes, so first of all let's just write down the general second order equation. So the general second order equation, so I'm doing it for two variables. Okay, the general linear second order equation. Okay, so you do realize there can be second order equations which are non-linear also. Okay, so we are basically looking at linear second order PDE. Okay, now why linear? The point is this: see, generally what happens is studying a nonlinear equation is generally difficult, and what we can do is essentially first of all try to understand how the linear equation works, and then there is a process called linearization which you can use on a nonlinear equation around some points and make it linear. So basically it will behave like a linear equation. So it is very important for us to understand how the linear equation works. So it should look like this: I j equals to 1 to n sum. So I am using the summation convention, and this is aij, okay, and uxi xj. I will give you some examples of what this is. This is a little complicated expression, but I will make it easy with some examples. So xi plus some ab, maybe I don't know, maybe let's say f times u equals to g. Let's just do it this way. Okay, now here there are some assumptions. So where aij, so this is basically a matrix you can think of. Aij, okay, sorry, aij, this matrix is nothing but a symmetric matrix. So that is aji. This is what we are going to assume, and we are also going to assume that aij, so this is for all ij, bi, f, g, these are all real valued smooth functions, real valued smooth functions. Of course, there is another assumption that aij are, I mean, at least is non-zero for at least one ij. So is non-zero for at least, some I and j in this set 1, 2. So essentially what I am meaning is this: you see, if all aij's are going to be 0, then essentially our this term is not there. Once this term is not there, then it can't be a second order equation. Okay, right? And why we call it a second order equation? Because you see, this is the highest order derivative which we have, uxi, uxj, this two order, right? So that is why we call it a second order equation. Okay, now again, this is a general form. So this is a general form. Let's write it like star of a second order linear PD. And why are we calling it a general form? Because I mean, you can put any linear second order PD in this form. Okay, and so of course I am assuming it to be smooth function. They don't need to be smooth, but for our, I mean, you know, this at least for this theory part, we are just going to assume it is smooth. Okay, another thing is, please understand this: we are essentially looking at a two-dimensional setting. Yes, so two variables, two independent variables. So the variables here are, you can think of it like x1 and x2. These are the two variables which we are basically looking at. Of course, you can talk about x1, x2 and x3. Yes, and this equation becomes a much complicated expression. Why? Because you see here, let's say this expression, if you just break it up, so it becomes a11, right? a11 ux1 x1, right, plus a12 u of x1 x2, yeah, you see, plus a21 u of x2 x1 plus a22 u of x2 x2. Okay, so you see there are like 4 terms which actually is contained in this particular summation, right? Now in 3 dimension, what happens is you have this a11, a12 and a22, a33, all these expressions are there, like from 9 terms which are involved there, right? So you do realize that the more dimensions you go, the higher dimensions it is, the complicated it becomes, right? Okay, now the point is this: see, first of all, what we want to do is we want to solve this problem, right? Now, generally speaking, given just a arbitrary ABC, it is not possible to solve this problem. Yes. So what we do is this: first of all, what we mean is, by solving this problem means, what is the meaning of a solution? Let's just write down what is the meaning of a solution. So for now, solution, we mean that, see, if there is a u, let's say, yes, you see G is smooth, right? F is smooth, Bi's are smooth, AI, BE are smooth. So for this expression to make sense, UXI, so basically you see for this expression to make sense, UXI XJ must be continuous, at least must be continuous, right? So if UI XJ are continuous for all IJ, so it means U has to be C2. Is it okay? Yes, that's the definition which we are going for. And of course, this is defined in some domain omega. So omega subset of R2 we are assuming, and here we are also assuming omega is open and connected. Okay, this is just an assumption which you are starting out with. Of course, connectedness is not required right now, but we are just going to assume it. Yes, so this is something which we call the domain. What is a domain? Any set which is open and connected. Yeah. Okay. Now let's look at the solution of it. See, what do I mean by a solution? So basically, we are looking for a u in C2 of omega. Okay, C2 of omega, such that star holds for all xy in omega. Xy in omega, right? So basically, this relation, the star relation, that should hold for all xy. Sorry, xi yi. Sorry, I'm using xi yi. So x1, x2 for all x1, x2 in omega. So if that happens, then we say this is a solution. So basically, we are looking for a twice continuously differentiable function such that the star holds for all xy in R2. Sorry, omega, right? Which is subset of R2. Okay, so now the point is this. See, we wanted to solve it, right? And to solve it, there is this very simple, I mean, nice result. And what it says is this: essentially, this is a very complicated expression, right? But this is in a particular setting. You see, this here, this is our setup. We are doing it in the variable x and y. So that's our coordinate. Now, what happens is, this has been seen that if you can change the coordinate, so let's say x1, x2, so let's say if you can translate it, or translate it means you can translate it like x1 going to x1 plus h and x2 going to x2 plus h. You understand? So essentially, what x2 plus k, sorry. So what we are doing is this. See, initially our, let's say, origin is the starting point, right? We start everything from origin, right? Now what we are doing is we're shifting the whole frame, this xy frame, to a new point. Let's say here somewhere it is hk. So we are just moving everything to this new frame. You understand? So this whole frame is going to this new frame. Yeah. And what happens is, we will see that under this particular sort of, so this is one way of looking at it. There are other expressions also. So basically what I'm trying to say is this: there will be a change of variable, right? So what I mean is, there is a change of variable, okay, which may help us, not may, it should help us, actually help us to deduce star. So okay, reduce, not deduce. So reduce star, okay, to a much simpler form, okay. Now, what do I mean by this? Let me put it this way, simpler form. So first of all, we have to understand what are the simpler form. So let me give you some examples of star. What are the examples of a second order equation number A? So let's say the general equation I'm giving. So you have this Laplacian. What is this? Laplacian of u. And how is it defined? It is u of x1 x1 plus u of x2 x2. And this is equals to 0. This is called the Laplace equation. Right? And we are going to study this equation in details for the next week. But essentially, this is the equation. Yeah. Now the point is this: what do with Laplace equation? See, what is happening here is this. Here, if you look at it here, what is happening? Maybe I can put it here. If you compare it with the star, so Aij is nothing but 1 and 0. 1 when I equals to j. Okay, and if I not equals to j, it is 0. So basically, then you see Aij, this expression, the second order equation reduces to this. Yeah. What about Bif? And here Bi equals to f equals to g equals to 0. So all other expressions are 0, and this is what you are left out with. This is called a Laplace equation. Of course, g can be here. You can actually have a g. Then also that is another example. So all of this is valid, but for now, let's just stick with the most simple form. Okay, let's look at another form. The another form looks like this: ut minus Laplacian u equals to 0. Yeah? This equation is called the heat equation. Yeah? Of course, it's a parabolic equation, but we did not talk about it. So, we'll talk about it later. So, this is a example of a heat equation. Now, if you want to break it up, basically it will look like this, ut. Huh? So, in this case, you see, this is another variable here. Yeah. So, what we are going to do is basically we can write it like this, ut, okay, minus Laplacian of u, okay. So, here we will change this form a little bit. Yeah, this is a, you see, the expression Laplace of u contains two variables, x1 and x2, and this u, so basically here u will be a function of x1 and x2. These are the space variables, and there will be a time variable t. Clear? Okay, time variable t. So, and then this Laplacian of u when we are writing, so this will be with respect to u x1 x1 plus u of x2 is it okay? And then that will be equals to 0. So, this is also a linear second order equation. Yeah. So, in this case what happens is you really can't put it in two variables. This is basically a three variable equation, because what are the variables? T, x1 and x2, three variables. Huh? So, this is called the heat equation, and this is the linear PDE, linear second order PDE. Of course, second order, why? Because highest order is 2, second order PDE, but in three variables. Variable. Now, you see, just a little change can actually make this equation in a two variable setting. So, the two variable function, 2D version, how should it look like? You see, you can just change it like this. This Laplacian, we can write it like this, ut minus u x1 equals to 0. So, this is called the one-dimensional 1D heat equation. Why 1D? Because, see, the time variable is always one variable, that is just one dimension t. x1, x2 can change. So, here x2 is not there. Essentially, we are just looking at x1, just a one dimension, right? So, essentially the space dimension is 1, that is why it's called a one-dimensional heat equation. And here, you see, this is an example of a linear, okay, second order PDE in two variables. So, exactly the similar sort of thing in star. So, here you can compare this thing with star, and if you compare what are the AIA, so basically A, if you can think about it, A11 is going to be -1, and then Aij is 0 for all other ij's, okay. And moreover, Bi, if you just look at it, Bi, so B1 basically, you can think of it like this. You see, B1 is equals to 0 and B2 is 1. You see, if B2 is 1, so basically you have U x2 or ut if you want. So, you see, here x2 I am writing as t. So, you can write it like this, and of course, here f and g is equals to 0. Yeah. Okay. So, what I want you to do is please go back, yes, and just try and find out what are the coefficients which actually give you this equation. Yes. Okay. Is there any other equation? So, this is the two part. One is the Laplace equation, one is the heat equation. There is another equation which is called a wave equation. Yeah. There's a reason why we are always concentrating on this thing. So, one-dimensional wave equation, let me write it, because that will be in two variable. So, it will be u tt minus u x1 is equals to 0. Okay. So, this is one-dimensional wave equation. Okay. And essentially here, see, if you think about it, Aij, okay, Aij is going to be -1 for I equals to j equals to 1 and 0 otherwise, okay. And this is Aij, and if you compare what is sorry, this has to be changed a little bit, 0, so equals to 1 if I equals to j equals to 1, and this is equals to 1 for I equals to j equals to 2, right? So, basically here if you look at it, you see here x2, we are writing x2 as t, okay. So, essentially, and then 0 otherwise, so this is fine. So, again, please take this part. So, utt minus ux1 x1 equals to 0. This is one dimensional wave equation. Again, why one dimension? See, t is always one dimension. This is the time variable basically. And the thing is x1, this is in r. So basically one variable. Now you can generalize this thing and you can write it as two-dimensional wave equation, which will look like this. This is the two-dimensional utt minus u x1 plus u x2 equals to 0. Okay, so that will look like this, utt minus Laplacian of u equals to 0. So this is also called a wave equation, right? And it is a two-dimensional. So this is a 3D. So the total thing is in 3 dimension, but we will call it a 2D, two-dimensional wave equation. Why two-dimensional? Because the space variable is in two dimensional wave equation. Okay, but this does not form in star, not in star. Okay, not in star, because in star is for 2 dimensions. This is 3 dimension. Yeah, 3 dimension means the total number of dimension is 3. Here you see in star the total number of dimension is 2. Okay, so that's about it. Now the point is this: what we are going to do, as I told you, what we wanted to do is we wanted to make a change of variable, which actually makes our life easier. So we, things look much simple. Okay, to do that, what we are going to do is we are going to start with the classification of PDE. Yeah, so the classification of PDE. Okay, so what does that mean? Let's just write it down. So if let's say you remember your conic sections, right? We are going to use the same sort of idea for conic section, and we are going to classify the this form, this star in that form. Okay, so let me write it down. So first of all, this the general form star can be written as let me write it in a much simpler form, which is much easier to comprehend. A u x x plus b u x y plus c u y y plus d u x plus e u y plus f equals to 0. Yeah, if you look at it, you see, since this symmetry part is there, you can actually reduce the whole thing down to this. Of course, a b c d e and f, they are all smooth coefficients, where a b c d e and f are just functions of x and y, are functions of x and y. Is it okay? It does not contain any u. Functions of x and y, because of the linearity, right? These are functions of x and y. Okay, and smooth, are smooth. I hope this is clear. Okay, now see this, let's call this as double star. This is the thing which you are going to use. Now we call, so basically this star, double star, we can write it as this. So basically we call this a elliptic equation. So basically double star, this particular expression, this equation, we will call it a elliptic equation. Okay, if see, I will just look at, see, basically in this problem, what you have to understand this, that the highest order term plays the important part. Okay, the lower order term is there, of course, that influences the solution, but the thing is, the behavior of the equation actually is only determined by the higher order term. That is why higher orders are important. Okay, so elliptic equation, when is it we call it an elliptic equation? You see, let's say it is elliptic at a point x naught y naught. So maybe I can write it like this. Double star is elliptic at a point x naught y naught if b square x naught y naught. So basically you see this b, these are function of x and y, right? So you take that and you square it up, minus 4 times a times x naught y naught, and then c times x naught y naught. This is going to be, let's say, negative. This is going to be negative. Okay, so then you have something called an elliptic equation at that point. Okay, so now the thing is this b, again the equation double star is parabolic. When is it called parabolic? At the point x naught y naught, at x naught y naught. If this expression, so see, for now what I am going to do is I am going to write it as delta. Delta is b square minus a times c. So delta is a function of x and y. delta is a function of x and y. Okay, so you see, if delta at the point x naught y naught, okay, if this is 0, and C double star is called hyperbolic. This is just a name, don't worry about but the thing is, this is a very standard notation which we are going to use: elliptic, parabolic and hyperbolic, because of the conic section thing. You see, this looks very much like a conic section thing, and we are getting that idea from there. So at the point x naught y naught, if delta at the point x naught y naught is going to be positive, is greater than 0. Okay, so let's look at some examples of elliptic, parabolic and hyperbolic equation. Yes, so you see the last 3 examples which I gave, this Laplace, heat and wave, those actually are the prototypes of a elliptic, parabolic and hyperbolic equation. Yes, so I will give you an example. I will see why this is true. Okay, so first of all, you see, for a Laplace equation, let's say, what is the equation? We have the equation, right? Let me write it like this: uxx plus uyy equals to 0, right? Ux, here I wrote it in terms of x1, y1, x1, x2. So, but I am writing here in terms of x and y. That's okay. It's just a variable. Now, here, if you can see, this is a equals to c equals to 1. If you compare it with the star, you see a and c is 1, b is 0, d is 0, e is 0, f is 0. So, b, d, e and f are 0. B, D, E, F, they are going to be 0. And by the way, we don't really care about what happens to the lower order D, E, F term. We just care about what happens to the higher order term. So A and C is 0 and B is 1. You see, this particular thing, this expression, okay, actually only depends on A, B and C. So we don't really care about lower order terms. Okay, so see, b square minus 4ac at any given point xy. So these are constant. So it is independent of the point. You don't need to do that. So it is 0 minus 4 times 1, which is minus 4, which is less than 0. So basically, this is a elliptic equation. And by the way, see, as you have already seen, that in this particular course, the next part of the courses, we are only going to talk about Laplace, heat and wave, right? Wave equation. Why we are doing it? This answer lies in this lecture. So essentially, why we are doing it is basically any expression which looks like double star, right? That's a general form. You can actually reduce the whole thing down to a much simpler equation, which actually looks like a variation of Laplace or a heat or a wave equation, right? And these kind of equations we know how to solve. That is what we are going to do it later. But the thing is, we will know how to solve it, and then we will use that idea. Do you understand? So we don't have to solve every possible problem. We just solve those 3. Okay, so that is one example of an elliptic equation. Now, can you give me an example of a heat equation? Let's look at heat equation. What sort of equation is it? Heat equation, if you remember, it is ut minus uxx equals to 0. I'm just doing it for 2 dimensions, 2 variables, not in 3 variables. This does not work in 3 variables. Whatever I'm doing, the classification is for 2 variables. So here you see a equals to minus 1, b and c is equals to 0, and ut, this is for the lower order term. We don't care about lower order terms. Okay, and therefore b square minus 4ac, as you can see, it is going to be, so b and c are going to be 0. So this is 0. So that is a parabolic equation. Okay, and we call it a prototype of a parabolic equation. Prototype means, you see, generally speaking, if you have a complicated second order equation which is basically a parabolic equation in its behavior, you can actually reduce it to something which looks like a heat equation, plus of course some lower order terms, but it will look like a heat equation. Okay, let's look at an example of the wave equation. What sort of equation is that wave equation? So you see, utt minus uxx equals to 0. So this is the point, and in this part, what is a is minus 1, b is 1, and c is 0, c is 1 and b is 0. Okay, so that will imply that b square minus 4ac is nothing but 0 minus 4 times minus 1 times 1, which is 4, which is positive. So this is an example of a hyperbolic equation. I hope this is clear. Equation. Okay. These are the prototypes. Yes. Now let me give you another last example. So let's say we are not taking simple problem like this. So D. Let's take this example. Let's say x square uxx plus y square uyy equals to 0. Clear? That's the equation. Now what I want to do is I want to write down this equation. I want to see whether this is a parabolic or a hyperbolic equation. First of all, this is a linear equation, second order, absolutely no issues. Okay, so what is a of xy? See, a and b, these are all functions of x and y. So this a of xy is nothing but x square. Okay, if we want to make it complicated, let's just write a x here. Let's make it a little complicated, no issues. And b of xy, here it is x times y square. X times y square. Let's just put it. Let's see what's happening. Sorry, not b, c. Yeah, let's please keep this in mind. And b in our example is corresponding to uxy, which is 0. If you want, we can put a uxy also, plus uxy equals to 0. Let's look at this equation. It's much complicated, right? And in this case, b is 1. Okay. Now you see, we need to calculate the discriminant, which is b square minus 4ac. And what is b square? It is 1 minus 4 times x cube y square. Okay. Now you see, based on whether, so essentially, if this is 0, when is this 0? So this is equals to 0 if on the curve x cube y square equals to 1/4, right? On that curve, there is some curve which is x cube y square equals to 1/4, and that curve it is 0 to 0. And of course, it is greater than 0 in the region set of all those xy in omega, or in this case, it is basically in whole of R2, such that 1 minus 4 x cube y square. So basically positive, right? Positive is in this case hyperbolic. So this will be your, in this region it will be parabolic, and then in this region it will be hyperbolic equation, hyperbolic. And what is this? It see, this has to be positive. So when this is positive, that means that essentially you want 4 x cube y square should be less than 1 in that region. Yeah, and it is negative for this region. So basically xy in R2 such that 4 x cube y square is greater than 1, whatever that region is. Yeah, we don't care, but there is some region which looks like this, and in that region this is elliptic. Yeah, so you do realize that this actually depends on the point x and y where we are choosing it, and the equation may have one equation depending on the region, may behave like a parabolic equation, may behave like a hyperbolic equation, or may behave like an elliptic equation. That's the point. Yeah. Okay. Now let's look at it. What are we trying to do? As I told you, there is this change of variable which actually reduces the whole problem to a much simpler problem. So let's understand that particular thing. Okay. So what is our equation? So our equation, so let's say we start with this equation, right? auxx plus buxy plus cuyy plus dux plus euy plus defu equals to g. That's the simple equation. So let's call this as 1. For now, let's call it a 1. Maybe the other problem I wrote it properly, right? Sorry. This I should write it as fu equals to 0. Yes, I missed a u here. Okay. Anyways, so fu equals to g. G can be 0. It's not an issue. I'm just writing the most general form. That's all. G can be a constant for all I want. Okay. So now, see, we wanted to transform this equation into a much simpler equation. So we have this new variable. So introduce new variables. What are the new variables? So basically, we are introducing xi, which is a function of x and y, and eta, which is a function of eta, again x and y. Okay, so as an example, let's just understand what's happening. See, our initial problem is in xy. Now let's say if I'm doing this change of variable x plus 1, so x I'm changing it to x plus 1, and y I'm changing it to y plus 2. Yeah, it's a translation essentially. What am I translating? If you think about it, I'm translating the whole frame. This frame is getting transferred to here. So basically the origin 0, 0, it's getting transferred to 1 and 2. Is it okay? Now this is a change of variable, right? And so what is xi and eta in this case? You see, xi of xy in this case is nothing but this x plus y, okay? Sorry, x plus 1, and eta of xy is nothing but y plus 2. In this case, this is, I mean, in our case, xi and eta will represent something like this. You understand? That's the point. Yeah, it doesn't have to be x plus 1. It can be xy. Y. I mean, you can look at this sort of, I mean, change of variable also, y square, let's say. All of this is valid. But the thing is, what I'm trying to say is this. This is an example of how xi and eta may look like. Okay, right. Now the thing is this: for it to be a valid change of variable, we need some expressions. See here, the first thing is this: we first of all introduce two variables like this, and here, and xi and eta, where should I write it like this? Where xi and eta are C1 continuously differentiable. It means the first order derivatives, all possible first order derivatives exist, and they are going to be continuous. Now, this particular thing, this is a valid change of variable, if you see the Jacobian matrix of xi and eta. So how do we write it? You xi x, xi y, eta x and eta y. Okay, this Jacobian is non-zero. Okay, in the region under consideration. So basically, let's say you are looking at a particular region D. So in that whole region, that has to be non-zero. That's the expression. Okay, if that happens, then xy can be determined uniquely. Yeah, for this system 1. So basically, sorry, for this system, let's call it 2. So if this happens, then xy can be determined. Xy may be determined uniquely, by 2. Okay, so let us just take a moment and try to understand what that Jacobian non-zero looks like. I mean, what does it mean? See, let's say that you have a x comma y, right? Yeah, and you are changing it to x plus some constant a and y plus some constant b. Yeah? Now let's understand if that particular thing is a valid change of variable or not. Yeah. So in this case, what is xi? Xi of xy is nothing but x plus a. Yeah, and eta of xy is nothing but y plus b. Yeah. Now you see, if you look at the Jacobian matrix, it is xi with respect to x, which is 1, and then xi with respect to y, xi with respect to 1 is going to be 0, and then eta with respect to x, eta with respect to x is going to be 0, and with the eta with respect to y, 1, which is 1. So that is non-zero. So this is a valid change of variable. Yeah. Now there is a question I wanted to answer, and this is a very, very simple question. Give me an example. Give an example where the Jacobian matrix is 0. Example where the Jacobian is 0. Okay. Now, how do you find something like this? I'm not going to do this, but I will tell you what to do it. Very simple, right? See, if this is 0, what happens? So xi x times eta y minus xi y times eta x. This has to be 0. So for now, this is xi and eta are like any, I mean, C1 functions, right? So if you choose xi in such a way that one of the expressions get lost. So basically, let's say xi of xy is basically only y. So in this case, this term is not there. So xi x is 0. This term is gone. So basically, in this case, you have eta x times xi x times, what is eta with respect to y? It is 1. This is equals to 0. So basically, eta x equals to 0. So that will give you, eta is a function which is independent of x. Yes. So let's say this is 1. Okay. You can write it as a constant 1, right? So the change of variable. So let's say if I am changing it to this xy going to 1, xi and eta, right? Xi is 1 and eta is y. Now you see, if you look at the Jacobian, this particular thing becomes 0. Okay, and the Jacobian becomes 0. So essentially, this is not a valid change of variable. Is it okay? Okay. Now, I don't want to put more pressure on it, but the thing is, one thing I will let you know. What happens is, in this basically changer variable, if you look at it, a square, yeah, in this changer variable, a square will remain a positive. So basically, let's say this square has a positive area, right? After the change of variable, that should have a positive area. It should not, the area should not become 0 after the change of variable. Yeah. So in this case, what happens is, in the original xy plane, let's say if you have a square which has some area, let's say a square, huh? And in this the modified change of coordinate, what happens is that gets to be a different, it becomes 0 actually, yeah, the square. So basically this is not allowed, we don't want that to happen. Okay, so that's the idea. Change of variable should have this expression, clear? Okay, now if you, okay, one thing, if you need to know, if you want to understand this much better, what is happening, why this change of variable needs this, you can look at the vector calculus book by Marsden and Randa. Calculus book by Marsden and Tromba. Extremely good book, huh? You can try this book. Okay, so now with this change of variable, what happens is we can write down this one in terms of xi and eta. That is what we want to. So what happens to u of x? See, if u, what is it? Xi is a function of x and y, and eta is a function of x and y. So basically, we need to find what happens to ux, uy, uyy, all these things, right? So what is ux? It is nothing but u xi x plus uy, u eta x. Okay, and similarly uy becomes u xi y plus u eta y. So these are the things. This is basically chain rule. If you know your chain rule, this is how. If you don't know, you have to go through it. It is very, very important to do, I mean, know how to work with chain rule, because otherwise you can't do this part. Okay, and similarly uxx is nothing but ux with respect to x. So basically this whole expression with respect to x, and I'm just writing it down, but you can of course check it. It's not very difficult to do. It becomes u xi x square plus 2 u xi x eta x plus u eta x square plus u xi x plus u eta x. Okay, and similarly u of xy, this expression can be written like this: u xi. It's a little big, huh? So please stay with me here. U of xi eta xi x eta y plus xi y eta x, okay, plus u eta x eta y plus u xi xy plus u eta xy. It looks very big, I know, but let me just do everything, and we'll see that how it makes our life much easier. Doesn't look like easier now. U xi y square plus 2 u xi eta y plus u eta y square plus u xi y plus u eta y. So please check this part. Check. It is very important that you check this. Very, very important. Why? Because we are going to use this change of variable in lot of different problems. I will show you, but that's the idea. Okay, so now once this is done, you see, if you substitute this c, ux, uy, uxs, uxy, uyy, all of this you can substitute in one. So substituting in one, you will get an expression. Substituting in one, we'll have an expression in terms of xi and eta. So it will look like this: a star u of xi plus b star u of xi eta plus c star u of eta plus d star u of xi plus E star u of eta plus f star u equals to g star. Okay, where what are the stars? Where a star is nothing but a psi x square plus b psi x psi y plus c psi y square. Okay, b star will be given by 2a psi x psi y. See, if you put everything here, then you will get this expression, and that is what I am just writing. Yeah, of course I am not calculating the whole thing, it will be just waste of time. But the thing is, you can always calculate it and check that whether this is true or not, and I will suggest you to do this. Plus 2c psi y eta y. Okay, and then you have c star, which is c star is what? It is a eta x square plus b eta x eta y plus c eta y square. Okay, and similarly there is a d star and e star, those terms are there. Okay, so similarly d star, find out this, what is d star, what is e star. We are not writing d star and e star because for this part to work we don't really need it, and you can check f star is going to be f and g star is going to be g. So this d star and e star I want you to find. It very much looks like a similar sort of expression. Please try it. Now, why are we not calculating d star, e star? There is some d star, e star. We don't care, because the thing is this, we want to see what happens to this. I mean, we had 1 and after a change of variable we got 2. Now we want to find out what happens to 2. I mean, what is the relation between 1 and 2? See, let's say that if you look at 2, the discriminant of 2, we can check. So again, another part. Again, this also you have to check. See, this is important because the thing, for solving the problems we need to do all these things. So it will be a practice for you essentially. So you see, b star, the square of that, minus 4 a star c star. If you just calculate this thing, yes, that will be nothing but the Jacobian matrix, the square of the Jacobian matrix times b square minus 4 a times c. Yes, you can easily verify this thing, absolutely no issues. It's just a calculation part, a little bit, but I mean, this is always true and you can easily find it. You see, what's happening now is this: since the Jacobian is non-zero, let's say, and this Jacobian square is going to be positive. So remark, see what we have is here is this. Let's say that the Jacobian is of course not zero, right? So basically that means the Jacobian square is always positive. Yeah. Now let's look at this expression. So from star, what we have is this. You see, if our original expression, so let's say this one, we can calculate what b square minus ac is, and let's just figure it out that in some region it is going to be elliptic. So if b square minus 4ac, so let's say like this. So if it is elliptic equation, b square minus 4ac initially is going to be negative, right? So if this is negative, j square is positive. So this positive term, negative term, it becomes negative. So b star square minus 4ac star c star is also going to be negative. So elliptic equation remains elliptic. You understand? Now if it is parabolic, this b square minus 4ac is 0. So basically b star square minus 4ac star a star c star is also going to be 0. So it remains parabolic. And if it is hyperbolic, b square minus 4ac is positive. So the modified discriminant is also going to be, the modified discriminant, which is this, is also going to be positive. So essentially what we are trying to say is this change of variable does not change the behavior of the original equation. Okay, right? So from star, the change of variable COV does not change the behavior of our original equation, okay, original equation. So essentially what happens is this, the behavior remains same. So if it is initially it's a elliptic equation, it looks like elliptic. If it's a parabolic equation, it becomes parabolic, it remains parabolic. If it is hyperbolic, it remains hyperbolic. Okay, and the thing is this, we have this expression. Now you will tell that what is the difference between 1 and 2? It looks much complicated too. It's not. See, what happens is this change of variables xi and eta, you do realize that are not going to be unique, right? There can be many change of variables which looks like this. Yes. Okay. So if there are more change of variables which looks like this, you can have a much simpler change of variable, like this sort of thing what we did. And in this sort of change of variable, what it does is it makes this expression 2 much simpler. Okay, so and once you have that, then we can just solve it, and you can find out your solution. It makes your life much easier. Although it looks difficult, it actually becomes much easy. So what I'm going to do is, in the next lecture, we are going to start with some canonical forms, how to deduce all of this. With this, I'm going to end this video. Thank you.